I have one tiny example. We have one object which is one. You can use it as one. Sigma basically is the one-dimensional module where I don't expect it to produce anything. Okay, but maybe we'll give a sign, something like that. Not more than that. About the construction of CFT correlators.
Right. Thank you. So thank you for the introduction. Thanks to the organizers for giving me the opportunity to speak. Maybe just a small comment. I'm now in Bonn and no longer in Hamburg. And today I want to talk about joint work together with Ingo Runkel, which will basically be some parts of a spoiler of Ingo's final lecture tomorrow, but also how you can go beyond the semi-simple setting which Ingo was discussing or is discussing in his lecture. And I want to start with a slightly different motivation than the one Ingo was giving, because Ingo was already giving us motivation from the perspective of this construction, where we were asking how you can go from a chiral CFT to a full CFT. And I want to take a slightly different perspective, was motivated from a slightly different perspective, via the so-called symmetry topological field theory framework or symmetry TFT framework, which has recently become quite popular in the physics community, but also some parts of the topological field theory community. So the basic idea behind this framework is that the generalized symmetries of a d-dimensional quantum field theory should be encoded in a d+1 dimensional topological field theory. And when I say generalized symmetries, what I really mean are the topological defects of this quantum field theory. And we saw some aspects of this in some of the talks yesterday as well. And sort of the idea behind this whole framework is that you have your d-dimensional quantum field theory, and the d+1 dimensional topological field theory acts on it via the topological defects in the d-dimensional TFT. And moreover, it's expected that you can actually reproduce a lot of information about your d-dimensional quantum field theory by instead considering a system in one dimension higher, which is just taking a cylinder over whatever you did before, but in the bulk you have just the topological degrees of freedom. On one boundary you have the actual quantum field theory, and on the other boundary you have a topological boundary condition, and then you can do this sort of dimensional reduction. And this should somehow give you back.
Can you explain for non-experts, so who is QFT? So I already used for CFT. I actually know who is TQFT.
Okay.
What is QFT?
In general, I don't know. And also, since this is only part of the motivation, this is more of a general picture. And what I want to do in my talk as well is to sort of make this a bit more rigorous for CFTs, where we have a lot more technology available. So this could be, in principle, any d-dimensional quantum field theory. And for example, I know that people are using this for these higher dimensional supersymmetric gauge theories, but there's also ideas on how you can use it in some things like the standard model. But I'm very far from being an expert on that. But this actually brings me to the point, which is I want to try and use these vague ideas to understand full 2D CFTs. So this means we'll now be in the following situation where we have a full 2D CFT on one boundary. So we'll have some conformal manifold or conformal 2 manifold. In the bulk, we have our a 3D TFT, and on the other boundary, we have a topological boundary condition. And I can also start to tell you a little bit more about what the mathematical ingredients here are. For this, I will first need to tell you what I mean with a chiral CFT and then what I mean with a full CFT. So for me, a chiral CFT will basically consist of two pieces of data. First of all, a VOA, which describes the chiral symmetries, and then a modular functor, technically in this complex analytic setting as Ingo alluded to it, but I will use the same wish list Ingo used and hope that we can translate this into something topological. And it will later give you a definition of how this looks like from the topological perspective. Now, for a full CFT, on the other hand, we'll still have the same two pieces of information because we'll still have a chiral half of our full CFT, but we will also be interested in some extra pieces of information. And this is mainly a repetition of what Ingo was telling us today in the morning. So we will have the field content, meaning the Hilbert space of our theory, or what fields are in our theory. And here I'm using the notation which Ingo apparently doesn't like, with using the bar for thinking about the anti-holomorphic part of the fields. And maybe most importantly, also the correlation functions, which again, as Ingo said, should be elements in the chiral conformal block spaces. So this modular functor takes care of the chiral conformal blocks of the theory, which is also why I put the superscript chi for chiral here. But for our surface, we want to have the chiral conformal blocks not on the surface, but on the Schottky double with the correct field insertions everywhere. Okay, so now the question becomes, how are these pieces of information, which you can make mathematically rigorous, related to this picture up here? And for this, let me first restrict to the rational setting, so to the setting which Ingo is using, because in this setting, the representation category of the VUA will be a modular fusion category, which means we can construct a three-dimensional topological field theory via the Reshetikhin-Turaev construction. However, this 3D TFT is not the 3D TFT we would want to put on this side of the picture. And the reason for this is essentially because we constructed it from the chiral data. So this will more or less be a 3D TFT, which has just a chiral CFT on the boundary. So the correct picture is more or less the following. Instead of having the 3D TFT in the bulk, we will have, okay. So instead of considering the picture on the left, let us first consider the picture on the right. And let me explain to you how the two are related. So we have from the VOA, we get a 3D TFT. This will have the VOA on the boundary in some sense. Then we have the 3D TFT in the bulk. Let's ignore what's going on in the middle. And then we have another VOA on the other boundary. So how can we get back to the symmetry TFT picture? We get back to this picture by simply folding or unfolding this cylinder here. And then you also see that what was a topological boundary condition before now becomes a topological surface defect in the 3D TFT here. And it's quite unfortunate, Ingo got a little bit less far than I hoped, because otherwise you would have seen a very similar picture already today in his lecture, but you will see tomorrow. Yeah, tomorrow again. So of the whole punchline of this whole motivation here is you can actually make this picture fairly rigorous in the sense that you can use the data of the 3D TFT together with a topological surface defect in it to construct both the field content and the correlators. And this is essentially a very abbreviated or condensed version of the FIS construction, so of the Fuchs-Runkel-Schweigert construction Ingo is talking about in his lecture, which sufficiently summarized says that for a semi-simple or rational chiral CFT, surface defects in this 3D TFT of the Reshetikhin-Turaev type give you all possible full CFTs with this chiral CFT fix.
So the modules over F I think about associated to the surface defect. Is that like the different bulk things I think about as associated to rep V and rep V?
The different bulk F's here will come from the surface defect. Yes. So these will be different for different surface defects.
You can compute F from the surface defect.
Yes. Yes, you will get F from the surface defect, but you get more.
How do you label surface defect?
Right now, I'm not telling you. Right now, I'm just saying any surface defect does.
I just don't know what is surface defect.
So abstractly speaking, it's embedded two manifold with some labels, but I'm not telling you what the labels are right now.
That's what I'm asking.
In this formulation, it will be either module categories with a module trace or pivotal module categories in the semi-simple setting, or equivalently special symmetric Frobenius algebras. That one. So, yes. But I think maybe Ingo will say a bit more about this tomorrow. Because sort of what I want to tell you today is how you can extend this theorem to the non-semi-simple world by using the three-dimensional TFTs of De Renzi, Gainutdinov, Geer, Patureau-Mirand, and Runkel, which are the 3D TFTs Marco is talking about in his lecture. So in a sense, my talk will be a little bit of a combination of both Marco's and Ingo's lecture. Okay, so let me first explain to you what a modular functor is in our formulation and how you can get it from such a non-semi-simple TFT. And here, let me start with explaining first my notation, because it's slightly different than the one Marco used, and try to explain to you how this is related to what he was talking about. So this three-dimensional topological field theory, which Marco is talking about, can be used to construct a symmetric monoidal two-functor. So I know many of you here are not so familiar with higher categories. So what a two-functor basically does, it's the natural map between two categories. So a two category is a three-layered structure. You have objects, one morphisms, and two morphisms, and a two-functor, which is an objects to objects, one morphisms to one morphisms, and two morphisms to two morphisms. So this thing here will be an assignment from our source category, which is a version of a two-dimensional Bordism category, but now with a little bit more. It's not just a Bordism category, it's a Bordism two category to some category of linear categories. And this will essentially be a finite version of the two category of linear categories which Marco has used in his talk. Okay, so what are objects, one morphism, two morphisms here? Objects here are just closed one-dimensional manifolds, so finite disjoint unions of circles. One morphisms are Bordisms between them, so surfaces with parametrized boundaries. And now we also have two morphisms. And in contrast to Marco, we will not take Bordisms between Bordisms. We will only take diffeomorphisms up to isotopy. So these are related to the invertible Bordisms in your category. And on the target side, we'll have finite linear categories or finite linear abelian categories as Marco defined them yesterday. One morphisms are left exact functors. Don't worry about the details too much here. And two morphisms will be natural transformations. Okay, so what does our symmetric monoidal functor do? So it takes one circle just to the category C we started with. And a bunch of circles will automatically be sent to a bunch of copies of our category C because it's supposed to be symmetric monoidal. Now on the one morphism level, we want to get a left exact functor. And the way we get this left exact functor is very similar to what Hao Zhang was talking about in his talk. essentially the idea is here we have a bordism from 2 circles to 1 circle. And for every boundary component here, we choose an object in our category. And then we send this tuple of objects into the TFT state space, where we instead of boundaries now have the correct objects inserted. And if you think about this as representations of the VUA, then that's very similar to what we saw a few different talks. Yes.
So do I imagine this state space as being identified with the dual of the HOM or with the HOM for?
In this case with the HOM, and I should also mention for the experts here that I'm actually lying a little bit. The target is not lex explicitly, it's an equivalent 2 category consisting of pro functors, which is also the reason why you get a vector space here. Let's maybe not get into the technical details here. Okay, and then there's also 2 morphisms, which are just diffeomorphisms up to isotropy, aka mapping class group elements. So for example, the modular S transformation will get sent to, in principle, a natural transformation, but since we don't have any boundaries here, this will just be a linear map. So we will have mapping class group representations. And these are the mapping class group representations Ingo was talking about. And then there's some coherence conditions with cutting and gluing surfaces and so on. And maybe one more remark for the experts, together with a second paper of the same authors who constructed the 3D TFT, we can actually show that this gives you a 3-dimensional construction of Lubashenko's modular functor, which was constructed already 30 years ago, although in a slightly different.
3-dimensional means 2 plus epsilon.
Yes and no. What I actually mean here is what they showed was that the mapping class group representations are the same as the ones from Lubashenko. And what we showed is, because I didn't tell you how this becomes a functor, so how does composition work? And this is actually induced by this 3-dimensional bordism, this gluing bordism Ingo had in his lecture today in the morning. And we proved that this gluing bordism induces the correct gluing map. So
can you evaluate it on an arbitrary 3 manifold?
no, but you don't need to.
Okay, I agree that you don't need to. But that's why I
But
wouldn't
you need more than just cylinders.
Yes.
Because the gluing bordism is not a cylinder. Yes.
I know the
Yes. Yes. I just want to. Okay. So this was still part of the chiral CFT, and I should start to get a bit faster. We wanted to talk about full CFT, not just chiral CFT. So for this, we will actually use a slightly different bordism category. And the reason for that is because we want to be able to describe full CFTs in the presence of boundaries in principle, which means we will need to also be able to put boundary conditions of our CFT somewhere. Because right now we only have a bordism category where all boundaries are used as gluing boundaries, but we also want to have some free boundaries where we could put our boundary conditions. And for this, we use this open closed bordism 2 category or 2,1 category, where the objects are now just compact 1 manifolds. And our bordisms now have a decomposition of their boundary into a free and into a gluing part. So this green part here is where we would put the boundary condition of the CFT. And then again, we have diffeomorphisms up to isotropy. And maybe if you were wondering why there's such a weird spacing before, the reason is because we can also get a topological incarnation of the Schottky double, which takes a surface to its double. And in this topological setting, this gives you a symmetrical 2 functor again, which just takes, in the simplest case, your manifold to the manifold disjoint union with a orientation reversal. And if there is a boundary, then you have to identify on the boundaries. And the reason for that is that you want to work with conformal boundary conditions. So this is how we can encode what a conformal boundary condition is in this topological setting. Okay, and from now on, I will abbreviate the, okay. What you can do now is you have this you have two different symmetric monoidal two functors, one going from this Bordism category to this other Bordism category, and one then going to legs. So you can compose them. And I will abbreviate this composition by throwing away the subscript, the superscript. Okay. So now let me give you a brief overview of how you can get full CFTs from surface defects in this formulation, and how you can actually make this, and at the same time giving you a categorical definition of what a full CFT would mean in this formulation. So the statement of the main theorem is that for every surface defect satisfying some technical conditions, you get a braided monoidal two natural transformation. And what a two natural transformation does, it now doesn't only send just, it now sends objects to one morphisms and one morphisms to two morphisms. So what does this even mean? So first of all, what are the source and the target of this two natural transformation? The source, which I call delta K, is the trivial two functor sending everything to vector spaces and identities on vector spaces. So you could think about this as something like the trivial theory, while down here we have our modular functor from before. And now I want to at least give you a little bit of an idea why I should be allowed to call this correlators, because right now I'm just giving you a very abstract definition. So what does this have to do with CFTs, and what does this have to do with the data I showed you at the beginning? Okay, so as I said, for every object in our Bordism category, we'll get a one morphism here. So for every closed one manifold, we get for every one manifold, we get a left exact functor. And if you go through the construction, then you will find that it will be a left exact functor of this type. The details don't matter too much here. What matters more is a statement, namely that for every left exact functor is representable. And again, we saw this in one of the talks on Monday already. So what this means is for every one manifold, we get an object in some copies of our category. So for the interval, this will just be the category C. For S1, this will be C box, C bar automatically, but we will see this later again. So the takeaways for the monomorphism components, we get the field content. Now we will also have two morphism components. So for every Bordism here, for every surface, we will get a natural transformation. And it will be a natural transformation involving this functor up here, as well as a very similar one where you just put the object into the second slot and not into the first slot. The details on this don't matter too much, but what's maybe more interesting here is I call this correlators. Why should I call this correlators? One possible explanation for this name is if you look at the set of all natural transformations, or rather the vector space of all natural transformations, you can show that this is canonically isomorphic to the chiral conformal plug functor evaluated at the surface, but already with the correct field insertions put in. So just from this perspective, these correlators will live in the correct vector spaces abstractly. Maybe more convincingly.
Sorry, BLC is monoidal. Functor BLC is monoidal.
The functor BLC is monoidal, yes.
But you are saying natural transformation.
I'm also saying monoidal natural transformation, or braided monoidal natural transformation. Okay. There will also be some, so there's also some data relating.
Okay. Good.
Yes. Yeah.
What was delta K? Is your modular functor or?
Delta K is the trivial two functor, so it sends everything to vect.
Ah, trivial. Okay.
Yeah. So you should think about this as as the trivial theory in a sense. Okay. But what I wanted to say is that this was just the data, but this data also needs to satisfy some conditions. And these conditions are precisely the compatibility with gluing surfaces as well as mapping class group invariants, which Ingo explained in his lecture today. So this is really just a very compact way of rewriting what Ingo had on the board today, essentially. Okay, so how do you construct this thing? And now I'm going to spoil you for Ingo's talk tomorrow. In the original FIS construction, they get just the two morphism components by looking at the so-called connecting manifold. So the connecting manifold for a surface is just consider the surface, cross it with an interval, and if there's a boundary, then you need to mod something out, which is again related to this conformal boundary condition, but let's not go into too much detail on that. Actually, just as an aside, the aside Ingo had on the board today is an example of such a connecting manifold. But now, what we realized that in order to go to the non-semi-simple setting, you actually have to also do this for one manifold as well. And with this, we can construct our two natural transformation. So this is a two-step process. First, you take your one manifold and you turn it into this connecting manifold, and then later on you will turn this into a functor. So how does this look like for, I forgot to mention something very important here. This two or three manifold, so this connecting manifold, naturally comes with a stratification just by embedding S into the S times 0 plane. So we naturally have a surface defect or a codimension 1 defect in there more precisely. And if you do this for the interval, then you will find that you will get this cup morphism, but now with this interval embedded here, and I label this with the label for my surface defect, which I'm still not telling you what it is precisely. For the circle is a little bit easier. It's just a circle across a cylinder, but I view this as going from nothing to two circles instead of going from circle to circle. Okay, now the question is, how do you get the left exact functor out of this? Well, you do essentially the same thing as you did for the modular functor. So you again just cap this off and evaluate it with the TFT. And for this to make sense, coming back to Azad's question, you need an extension of the non-semi-simple 3D TFT, which knows what happens to these surface defects or to these codimension 1 defects. For the two morphism components, you essentially do the same thing. The pictures become slightly more complicated, and I think Ingo will be going into more detail on them tomorrow. So let me just show you how this looks like in the example of this whistle Bordism we had before. So first of all, where actually do the source and target of the natural transformation come from? The source essentially comes from the boundary components of this morphism. So this becomes this, the circle becomes this, and this will correspond to the two functors we had before, while the target over here is really what's coming from the surface. And now the components of our natural transformation are given by evaluating the TFT on this free manifold, and the surface defect here in the middle is really just a deformed version of this Bordism here. Okay, maybe this was a bit fast, but just to sort of get you back to what we had before, or what I started with, if you stare at just this tiny little part a little bit, then you will see that the picture, at least schematically, is very similar. And actually, if we throw away all Bordism, all open components, so if we only look at the bulk sector of the theory, then it's really just crossing with an interval, so we get into the cylinder situation we had in the beginning. Okay, and now you might say all of this was very technical, very abstract, so what's the use of it? You can actually compute stuff with this, which might be interesting, and now I can also tell other what's one possible label for the surface defect, which would be the monoidal unit in the category. And this will correspond to the diagonal CFT. I should also mention here that we also should put some boundary labels here in order to make sense of everything. And what's maybe nice about the whole construction is that you can very easily also encode topological defects by just putting some extra lines here on the surface. Okay, but now let me tell you something about an example. In this case, the boundary conditions and topological defects are again labeled with objects in our category C, otherwise it would be via module category. We can compute, for example, what the boundary fields of our theory are as objects in the category. And if we come from the representation theory of a BUA, then this will be some infinite dimensional vector space on which the BUA acts. And in this case, this would be boundary changing fields, changing a boundary condition M to a boundary condition N, or rather, not really boundary changing field, but boundary changing field insertions.
What are your assumptions on C now?
Right now, C is a modular tensor category.
So that's not new as compared to the FRS results. Or
No,
maybe something.
no. Oh,
It's semi-simple or what?
no, it's
If
not
it-
semi-simple.
Okay, it's not semi-simple.
No, it's not semi-simple.
Okay.
But in a sense, it's not new to other results of yours.
No, but
We
I
can
think-
also see that it's not semi-simple by looking at the bulk fields, which are given by this coed object. And in the semi-simple setting, this is really what Ingo had today in his lecture, which is just a sum of simple times simple dual, depending on your convention. So this is the natural non-semi-simple generalization. This sort of also goes to the question Chris had today during Ingo's talk, how you would get the field object and how you can split it up. In a non-semi-simple setting, you can't split it up in a non-semi-simple setting, but you can still work with it. You can also compute the boundary states of theory, and these will correspond to characters of your category or characters of the BUA. And all of this recovers results of Fuchs, Gannon, Schaumann, and Schweigert. But we can also do a little bit more. We can also compute what's the algebra of defect operators. And this turns out to be isomorphic to the Grothendieckring of the category by basically reformulating a result of Shimizu in this language. Okay, and with this, I'm already over time, so I'll just flash you some possible connections and outlook on what to do. Thank you for your attention.
Okay, other questions? Yeah, no worries.
Like I know a few examples of explicit correlation function which are composed by logarithmic as logarithmic coming from a Jordan structure. I mean, do you have this? I mean, can you arrive at this explicit correlation function, or I mean, can I plot them?
At the explicit
Big
correlation function, no, for essentially the same. Okay, even in the rational case, we can't get the explicit correlation function in the sense that we still need to have this comparison between the actual complex analytic conformal block spaces and the TFT state spaces. So that's in Ingo's wish list, this isomorphism, which is in a sense missing. In the rational case, we by now know a lot more, especially by the results of Lucas Voigt and Chiara Damiolini. But in the logarithmic setting, I think this is pretty open. But it would be interesting to, for example, compare it with the work of Bingui and Haoshan. So,
But what you should emphasize to Raoul is that your results give a proof of the existence of consistent
Yes.
correlators.
yes.
So Raoul might not care about this as a physicist, but as a mathematician, you should be proud of this result.
No, it's really about it.
Yeah, so it also gives you an explicit construction. Also, this second point here would be related to your question. So, for example, it would be interesting to look at explicit examples related to VOA. So, for example, to the symplectic fermion VOA or to the triplet VOA, which would give you a rep UQSL2. And at least for the triplet in the diagonal case, as far as I'm aware, there are results in the log CFT literature. And it would be very interesting to compare how our results match with theirs. But this is still something which is.
What kind of explicit calculations you have in mind?
I would need to look at the references.
No, you say explicit calculations. What explicit calculations you want to do?
What if this, for example, computing the 3-point function or the 3-point correlate for bulk fields. So 3 bulk fields on a disk.
Even from CFT point of view, or I mean,
From this TFT point of view, or for example, the partition function, and compare it to what people have done.
what do you mean by partition function from categorical point of view?
What do you mean with?
I mean, what it is partition function from categorical point of view?
The partition function from the categorical point of view would be the correlator for the torus in our setting.
I mean, vector space correlators, or what? Or what?
No. Actually computing this for the torus, essentially. So the two morphism components for the torus. This would be what I would call the partition function of the theory.
Did you compute it already? And do you get in the Cardi case the Cartan matrix of the category?
I can compute it in the Cardi case, but I still don't know how I can compare it to the. So there's essentially two versions you can compute it, and I'm not completely sure how I get the Cartan matrix out of it. Because the bulk in the open sector, you can compute way more things than in the bulk sector, essentially because the Deligne product is way harder to work with. But it should be the Cartan matrix.
Will be.
Concerning the existence, like, so you have a way of seeing it that. So, can you say? I mean, because now we are like we are in the moment we are exploring like CFT that goes beyond the minimal model. We're exploring non-unitary, and somehow we found some solution, but we don't know if they are unique or not. So, in order to tell that it exists a solution, maybe only one solution at a given set of charges, this method can help to at least like classify the number of solutions that we can look for. Like,
so this is
given respect.
It's not a classification result as it is in the semi-simple setting. It's just a construction. So it's an existence result. But also, I'm not completely sure which physical theories fit into this framework. So because we assume quite a few things on the VOA side still. So these will be C2 cofinite, logarithmic, but the representation category still needs to be rigid, for example, which is true for the triplet, but for these WQP models, it's no longer true, for example. But it would be interesting to see if we can extend it to this setting as well, but there we don't have the TFT technology available yet. and I don't know if the TFT technology.
Graphical calculus is a problem in that.
Yeah, the graphical calculus is a problem. Yes, I agree. And that's also why I'm not completely sure if it would work to lift it into a TFT.
But even in the rigid case, do you have, let's say, classification? Do you have some classification results in terms of what kind of module categories
No, so
you have to
okay,
consider?
so
Or...
the module categories we know how to work with all come from separable symmetric Frobenius algebras, which in a non-semi-simple setting is quite a big problem because separability is not Morita invariant.
Yes, yes.
So instead, what one should look at would be exact pivotal module categories. But for exact pivotal module categories, I don't know how to build a defect TFT. That's the problem. I sort of know how it works locally, but I can't globalize it in a sense.
Do you want this class of module categories closed under product?
No,
if you fuse two defects,
For this construction.
I would not need it.
there are other questions? Seems not the case. Thank you. No?
Thank you very much to the organizer for the invitation. So yes, I will talk about a joint project with Francesco Costantino, the stated screen TQFT. So let me just remember from Marco's lecture what is a TQFT. So a TQFT is a binding modular functor, and you go from some category of cobordisms to some algebraic category. Okay. And then to a surface, you will associate an object in the category, and to a cobordism, you will associate a morphism between the objects that you have associated to the surfaces. Now you have to remember that a morphism in a category is not necessarily a function, right, or an application. And indeed, here in our example, morphisms are not functions, but morphisms are bimodules. So what we will assign to a surface is an algebra, which is denoted SH of sigma. S is for a stated scale. And to a cobordism between two surfaces, sigma minus and sigma plus, we will associate a bimodule between the algebras corresponding to the surfaces. Okay? And then the source target of this category, so I will explain, but it is a category which is almost the same as Marco's lectures, right? This kind of cobordisms with cylinder boundary. And for the target category, the algebraic category, so it will be a category of bimodules, as you can see, but these bimodules also satisfy interesting properties, which are given by the topological properties of the cobordisms. Yeah, so the plan of the talk is the following. So first I will explain the source category. What three cobordism do we want to consider, and what is the definition of their stated scale spaces? Then I will discuss the algebraic properties of these spaces, and in this way we will discover the properties of the target category. And finally, I will explain also the relation with the Kerler-Lukashenko TQFT. So here it will be a bit a spoiler for the last lecture by Marco. So he will be a bit fast on what is Kerler-Lukashenko TQFT because he will explain it more in detail. Okay, so let me describe the categories. So I call it strip of arc. You will understand why there is arc shortly. For the object, so we consider connected oriented surfaces with one boundary component, so circle boundary component. And on the boundary, you have one marked point, okay, which is represented by this big black dot here. And the morphism, so the morphism are cobordisms. Right, so if you have now two surfaces of this kind, sigma minus and sigma plus, you will consider three manifolds M oriented, whose boundary decomposes into these three parts. So the minus part is of course your first surface, sigma minus. Okay, the top part here in red is the sigma plus surface, and then you also have cylinder boundary, which is depicted in this green cylinder. Okay. And then you require some natural axioms. So of course, the top and bottom boundaries are the surfaces. Then the ds of M is the side boundary, it is the cylinder. And you want that the boundary, the top and bottom boundary intersect on the cylinder at the circle boundary of the surfaces, okay, which is this. And of course, the two surface boundary does not intersect. And moreover, so there is a technical condition which explains the name of the category. We fix an arc. We fix an arc in the side boundary, which goes from one market point to the other market point. Okay. So if you remember our Marco's lecture, in terms of this category of key rectangles, this cobordism, you would draw it like this. So you remember Marco, we had this kind of diagrams with handles. Right? And here the cobordism that you see, it is this one. Okay. So this is just the same category. It is just that I draw the cobordism explicitly just to make it easier to see. Okay, now what is the structure of this category? So composition, it is as usual. You will glue along the common surface. Okay. The identity morphism are secant surfaces. So you take a surface sigma and you do the cylinder like this. And again, I draw it in this way because it is more easy to see. Monoidal product, it is a bit harder to see. So monoidal product, first you have two surfaces. So surfaces, you can put them in a bigger disk, right? You can just take a disk. You remove two little disks like this. Okay, you put points here. And you glue your surfaces here and here. Okay? So this is monoidal product at the level of surfaces. And for cobordism, you do the same things, but you glue now in a cylinder, okay? In a cylinder like this, without the cylinder inside, okay? And you get monoidal product like this. And the monoidal unit is, of course, the disk. Okay, so I think there's a picture for the monoidal product. Yes, another view. So you see, you take this disk minus two disk, you take cylinder, then you get this picture, and you glue your first cobordism here and your second cobordism here. And this is what we call the monoidal product. And of course, cobordisms are up to diffeomorphism. And finally, there is braiding on this category. So braiding, you can imagine it in this way. So you take your two surfaces that you have made monoidal product, okay? So they are in a disk, and you have two pieces, and now you braid them like this, okay? So if you braid these two surfaces, you will get this image here, which is indeed a cobordism from sigma 1 tensor sigma 2 to sigma 2 tensor sigma 1. And it's easy to see that this satisfies the axioms of a braiding. Yeah, in this picture, of course, you have to forget the inner arcs and market points. Eh? So all what is dotted, the dotted arcs, you forget them, and the inner market points, you forget them. You only remember the one on the boundary. Okay, so in this way, you get a braided monoidal category, which is the source target for our TFT. Yeah, so this is, if you forget these arcs and marked points, you get exactly the same categories as in Marco's lectures. And this category has been studied by many people, which are listed here. And later we will see what is the main contribution of all these works. So it is that you have basically a presentation of this category by generators and relations, but I will come to this later. Okay, so now we want to define the stated scale space of three cobordism. So for this, I will first define what is a scale. So as H-color scale, gamma in three cobordism, it is an embedding of the frame embedding of circles and intervals. Okay, such that the embedded intervals, their endpoints are in the arc. Okay, so here you have the endpoints of the embedded intervals. You also have circle components. Okay, framing, it means that you have a little thickening all of this. It is not just strands, it is ribbons. Okay, and then the second condition requiring that the framing is vertical at the arc. It means that if you have a ribbon, the ribbon will arrive like this at the arc. Okay, cut at the arc transversally. And H-colored means that each connected component is labeled by some finite dimensional H module, okay? Like in Reshetikhin-Turaev ribbon graph invariant, the same kind of stuff. So these are more or less ribbon graphs embedded in three manifolds. Okay, and yeah, we allow coupons. So coupons, it is exactly like in Reshetikhin-Turaev formalism. You can have little boxes labeled by H linear maps, And of course, the H-linear map by which you label has to be compatible with the label of ingoing and outgoing strands. Okay, so this is for a skein. And now let's see what is a stated skein. So it's a state will be an element which is associated to the what happens in the boundary. Okay, so look at this example here. So here you have a neighborhood of the arc. Okay, and then of course when you look at neighborhood of the arc, what you see is that some strands which are arriving and others which are going into the surface. Okay, so here you have outgoing, ingoing, outgoing. You have also colors, x1, x2, x3. Then a state will be an element in this space. So here you have x1 outgoing, so it gives you x1. Here you have x2 ingoing, so you have x2 dual, and x3 outgoing, so you have x3. Okay, so a state will be an element of this vector space here. Because H is a Hopf algebra, I forgot to say H is a ribbon of algebra. So because H is a Hopf algebra, this is again a H module because you can use coproduct and antipode to act on such spaces. And a stated skein then is just a pair of a skein and a state. Okay, so in this example, you see what you have here is something which is ingoing. And if you follow the arrow, here you are outgoing. So you are in X dual and so X. Okay. Yeah, maybe a comment. So if for the state, you don't need to don't search a physical relevance to the word state. Okay, it's just a word like another. And just a comment also. Maybe some of you have seen this construction for quantum SL2. And then if for H you take a quantum SL2, then in this case, actually, you can color everything with the fundamental representation, C2. Okay, and C2 as basis, as a two-dimensional basis. So you can call the basis vectors V minus and V plus. And then in this case, the states are just signs. Okay. You just put plus or minus for states. Also, since C2 is self-dual, you can forget orientation. Okay, so this definition, in the case H is UQ of SL2, reduces to the ordinary stated skein space introduced by Ley for surfaces and by Costantino and Ley for three manifolds. Okay, so this is just a generalization of this. Yeah. Okay, so now we have to put relations among this. So to put relations, we will use the Reshetikhin-Turaev functor. So recall that H is a ribbon of algebra, which means that H mod, the representation category, is a ribbon category. And then for such categories, you have a Reshetikhin-Turaev functor, which takes a ribbon graph and which gives a linear map, actually a H linear map, between certain vector spaces. So here, if you consider this example, again, the resulting map will depend on what happens on the left side and right side, depending on the orientation of the strands. Okay, so you can see that on the left side, you see x1 outgoing, x2 ingoing, and x3 outgoing. So it will give you this source vector space. And on the right side, on the arrival, what you see is x5 outgoing and x1 ingoing, so it will give you this vector space. Okay, and here I have put an example with a coupon. So you see you have a small box which is labeled by an H linear map whose source and target depend on the color of the strands.
Do you need anywhere that you have a Hopf algebra?
Yeah, for Reshetikhin-Turaev functor you need. Or you need ribbon category.
For the states.
For the state you will need.
You need the fiber functor, right?
Your question is why I choose H mod?
Yes, rather than an arbitrary ribbon category.
For the states, because I need vector spaces to say a state is a vector in this space.
Your ribbon category just needs to be fibered over vector. Like
I think you can do this, but this is a generalization on which François is working. Okay, and then we can use this to make the definition of a stated skein space. So recall that for our three cobordisms, they carry an arc in their side boundary. Okay, and then we consider the vector space over the ground field K, which is fixed from the beginning, which is formally spanned by stated skeins. Okay, so you look at formal linear combination of pairs gamma and S stated skeins. Okay. and you put some relations, and the relations are given by Reshetikhin-Turaev functor in the neighborhood of the boundary arc. Okay, so here, if you are in the neighborhood of the boundary arc like this, then in general you will see some strands arriving, and close to the boundary you can have some interaction between these strands, maybe a crossing, maybe some twist, etc. Okay, and then also you have a state S, and you say, okay, I can erase this ribbon graph, but then I have to change the state. I have to change S with the state where you use the linear map associated to G by Reshetikhin-Turaev to act on S. Okay, and this makes sense by definition of the state, because the state will be exactly in the target space of Reshetikhin-Turaev of G. Okay, and here you will have a state which is exactly on the target of the Reshetikhin-Turaev of G, which is here. Okay, and then which correspond to these strands. And there is also some irrelevant relation telling that states are linear in some sense. You want states to be linear. I think there is an example to make this clearer. Yes. So if you look at this example, for instance, you can draw this little box, okay, which is a cube neighborhood of the arc. And then the ribbon graph that you see in this little box is this, okay? So here you will get an endomorphism because source and target have the same strands, okay? This will give you then this linear map, and you can act by this linear map on your state, and then you will get a new scale with a new state where this box has disappeared, okay? Actually, you can go further here because you can also use isotopy. So we have to realize that actually the scale relations, that they are not local. They are not only something near the boundary, because you can use isotopy to bring your strands near the boundary and force relation, okay? So here I can use isotopy to bring this crossing near the boundary and force a new relation, and then this crossing would disappear, okay? So because of isotopy, the relations are not local. You can force relations by bringing stuff near the boundary.
Why it disappeared? It's not identity, right? This morphism.
Which one?
No, but why have this relation again? Somehow this box disappeared.
But the state has changed now.
Huh?
The state has changed.
The state is changed.
Yes.
Okay.
So when you want to erase something, the price to pay is that the state changes.
State is it?
Yeah. It's the point. And again, here also, if you bring this crossing near the boundary, the state will again change. Other questions? Okay, so these are the vector spaces that we assign to three cobordisms. And now let's see their algebraic structure. So they carry a natural algebraic structure. So if you have a cobordism M from two surfaces, sigma 1 and sigma 2, and another cobordism N to sigma 2 to sigma 3, then you can do composition, right? Composition is just gluing along a common surface. And then, or at the level of skeins, you have a natural operation which is stacking. So you see, if you have a skein in N, and if you have a stated skein in N and a stated skein in M, then you can produce a new stated skein in the composition of the two, because you have natural inclusion of N into the composition and of M into the composition. And then you can just take this disjoint union of the two stated skeins. And for the states, you just do tensor product. And this is really seen to be an associative operation, okay, which we call stacking. So here is an example. So here, for instance, you have a skein in a cobordism from sigma 1 to sigma 1. Here you have a skein from a cobordism to the disk to sigma 1, okay? Then by doing the composition means that you identify the yellow part, okay? And you see that when you do this identification, you get this skein, okay? And by the relation, actually, the skein labeled by Y can now disappear, because by isotopy, I can bring it very, very close to the boundary arc, and I can use the relation. So actually, in the result, the skein labeled by Y could be erased. But the state would change, of course. And this implies, so this very simple observation implies important facts, which is that if I define SH of sigma to be the static case space of the cylinder for sigma, then this is an associative algebra. The stacking gives you an associative product. The unit element is just the empty skein. And if you have a cobordism between two surfaces, sigma 1 and sigma 2, then by stacking, you get a bimodule structure. Okay, so this construction gives you algebras and bimodules. Moreover, you have H equivariance, because you see that H act on states, because we say states are elements of a H module, because when you have two H modules, their tensor product is again an H module, and the dual is also again an H module. So it means that since the states belong to tensor product of H modules and their dual, a state is actually again an element of an H module, and then you can act on states. This makes sense, okay? And then you say, okay, the action of an element of the ribbon of algebra H on a stated scale is just the action of the states. And in this way, SH of M becomes a H module. Just a remark, the action is locally finite, meaning that every element has finite orbit, because the states are elements of finite dimensional H module by definition. So the action is locally finite. And it is very readily seen that you have this equivariance property, okay, which means that action of H is compatible with stacking. And here I use the Swidler notation for coproduct. So in your algebra, you have the coproduct delta, which is mapped from H to H tensor H. Okay, H tensor H. And since we don't want sum everywhere, we use this Swidler notation. Okay. And you have this equivariance property. And say differently, it means that you get actually algebras and bimodules internal to the category H1. And if you don't know what internal to H1 means, you can take this as a definition. Okay, so now we have quite an idea of what will be the target category of our functor. So you get algebras and bimodules internal to H mod. Okay, so it means that actually you land in this category BIM H. So the objects are associative algebras internal to H mod. The morphism are isomorphism classes of bimodules in H mod. The composition is the usual composition of bimodules, which is by tensoring over middle algebra. And the monoidal product is the tensor product of algebras and bimodules. So this uses property of the category H mod. Since H is quasi-triangular, which means you have R matrix, H mod is braided category, and then you can define tensor product of algebras and bimodules. Okay, so for instance, if you have two algebras, A and I prime, you want to define multiplication on A tensor A prime, but you see the braiding allows you to switch the factor, the two middle factors here, and then after you can multiply. And you can do the same thing for bimodules. If you have two bimodules, you will get a tensor product bimodule over the tensor product of the algebras. And here it is easy. Again, you just need braiding to switch the two factors. So in this way, you get a monoidal category. And the first theorem is the following. So the stated skein operation can be seen as a strict monoidal functor from the category of cobordism with arcs to this category of bimodules. So for the functor part, it was a Constantinole, and we proved the monoidal part. And functor means this, and monoidal means this. Okay. So these are equalities of bimodules. Yeah, so what about the braiding? Maybe a bit faster here. Yeah, so there is an operation of 3 cobs that we have not discussed yet, which is the braiding. Okay. So what can be said about the braiding? How does the stated skein functor interact with the braiding? So to answer this question, we need to introduce this object, the Cohen, which has already appeared many times in talk, so I will not give more details. But there are 2 important properties. This object is the Hopf algebra in the category, and there is also a canonical half braiding on it, which is defined by this universal property. Yeah. And because of these 2 operations, you have this definition of quantum moment map. So if you have A and algebra in H mod as before, then a quantum moment map for A is an algebra morphism from the Cohen to A, which satisfies this commutative diagram. Okay, so here you see you have this sigma, which is used to switch the factor, and then basically it is a commutation relation between the image of this morphism and elements of A. Okay, because you see here you switch and then you multiply. So it's commutation relation. I don't have time to make it explicit in terms of H mod, but it is just some algebra morphism satisfying commutation relation. And what is interesting?
If you take dual picture, would it be like full center, or
What in which sense?
if you take a not coent and if you dualize everything and those arrows in your previous picture?
For end, I think you can still define the. I think you can still define the sigma by reversing all the arrows in the diagram. But then I don't know if quantum moment map.
Trying to understand the meaning of this.
There is another definition
Can
of
we call it
quantum.
quantum moment map, or can you say something more about this?
There is another definition of quantum moment map which is easier to understand. So I can explain at the end if you want. Okay? Because this is the categorical definition, but this is an older definition which is easier to understand. I can explain at the end if you want, but I will just be short here, just to explain why this appears. Okay, this is because thanks to this quantum moment map, you can define a subcategory of beam H, where now the objects will be pairs. So you have algebra and you have quantum moment map for this algebra. Okay, and you see since the quantum moment map is a morphism from the coend to the bimodule. A bimodule becomes a bimodule over the coend also. And then you can require some compatibility condition, which is this one. Okay, so you see it is the same diagram as for quantum moment map, but now it is compatibility condition because you use action instead of multiplication. And you can make a subcategory which has this object and this morphism. And what we proved is that then this subcategory is braided because you can use these quantum moment maps to define a braiding. So now you have to remember that the braiding here will be bimodules. Okay, so what does it mean? It means that you have a bimodule which has to be a morphism in the category beam. Okay, in the category of bimodules, you want morphisms like this. We have A1 and A2 are algebras. Okay, and by definition, this has to be A2 tensor A1, A1 tensor A2 bimodule. So here the braiding is really a bimodule. Okay? And actually as a vector space, this bimodule it is just A2 tensor A1. And then on the left, you will just use the multiplication of this algebra. And on the right, here you will use, you see this is not in the good way. You have A1 tensor A2 and you want to act on A2 tensor A1. And then you will use the quantum moment map to switch the factor. So here you use the quantum moment map. And in this way, you can define a braiding on this category.
Let's say I start with a ribbon category, which is vect.
H is equal to C. I mean,
okay. So this is.
if vect, you see nothing there. Quantum
So in the case of vect, it gives nothing.
you see nothing.
And can you give some simple example? Take simplest ribbon of algebra you have in mind.
But you want what? You want an example of such bimodules?
Yeah, this braid bundle category. This beam QMM.
You want example of QMM?
Yeah.
Yeah. Okay.
QMM, yeah, of course.
Look, you look at this. The internal AND object, okay, which is V tensor V dual. This is algebra in the category, right? Yeah. So this is algebra, and you have QMM for this. So the coend as a vector space, it is H star. Assume H is fin dimensional, okay? And then you can do this. Then you want this. Okay. To a linear form, you want to associate function on V. Okay. And you do this. So this has to be function on V, okay? So evaluation of V will be this. It will be, you do this. You apply it to the monodromy matrix. This is element of H, okay? And then you act on V. This is quantum moment map for internal AND. This example.
So in your category, objects are what? Are algebras equipped with such?
In this category,
Quantum
BIM QM, yes.
So the objects are algebras.
Pairs, algebras and QM.
QM.
And QM.
QM is like a structure. Like
Yes,
a
yes.
given algebra might have many of them.
Yes.
It's like, okay.
Yes.
So this is just example of objects.
Yes.
Give, oh, okay, okay.
This is an object in this category. And if you want morphisms in this category, it's easy. You just take internal ops. These are bimodules in this category, because you can act on this and on this by these ones.
I also found them super confusing for a long time. So if you think of the stated skein algebra structure as coming from the action of some disk on your surface, then the quantum moment maps, a good way to get them is by acting by the annulus instead. The same
What?
An annulus instead, the same boundary component. And this is like a good source of them. That's what it makes sense.
Which is the boundary.
Okay. Yeah, and then so the theorem that we have seen before can be improved. So now with these braidings that we have defined, thanks to the QMM, we have actually, you see, restricted the target category, because SH actually takes values in this subcategory equipped with QMM.
SH was what?
The stated skein functor.
A functor.
Yeah, the stated skein functor, and it is a braided strict model functor. So with this braiding, it is the braiding corresponding to topology. Okay, and here you have the picture defining the quantum moment map on stated skein algebras. Time is over, so I will just pass. Yeah, just a few words on relation with the Kerler-Lewashenko TQFT. So Marco will explain all of this, but there is this theorem which tells you that actually you have presentation by generators and relation for this category, 3Com, okay? The generated object is just the torus, because if you remember, objects in our category are just surfaces with one boundary component, but this is just genus, right? So the genus G surface is isomorphic to G copies of the torus. So this is your generating object, and you have generating morphisms, which come from the fact that T actually is of algebra object in this category of cobordisms, okay? And moreover, you have certain special morphisms, so integral, co-integral, as Anna explained, and also other morphisms. So you have this morphism. You have morphism coming from the data, okay, product, co-product. So here, for instance, you have the product, you have the unit, you have co-unit, etc. Okay, and you have also extramorphism, integral, co-integral, and again, and also extramorphism, and you have list of relation. And this is presentation by generator and relation for this category. This is due to all these people, and this is well explained in paper by Bobcheva, Beliakova, De Renzi, and Pierre Galini. And it means that a braided monoidal functor out to this category in any category C is just the same thing as the Hopf algebra in C equipped with morphism, because you will say, okay, T maps to this Hopf algebra, and this morphism lambda, W, and tau, that they map to certain morphisms that you give. Okay, so you have complete classification of the QFTs out of this category, and in particular, you have the Kerler-Lewashenko TQFT. Which says, okay, if you have C which is reborn and also factorizable, which is non-degeneracy condition, then you get a TQFT by mapping T to the coet. So this is a modern point of view of the Kerler-Lewashenko TQFT. And then the relation with us is as follows. So you have this square diagram. So you see at the top you have Kerler-Lewashenko TQFT, at the bottom you have stated skein functor. On the left column, you have a forget functor, because for Kerler-Lewashenko, you need cobordisms with more structure, okay, with extra data. And on the right, it is interesting. On the right, you have a very stupid functor, which I have actually started to explain here. So you see, to any object in H mod, you can associate internal and, which is an algebra with QMM, okay? And to any morphism between V and W, to any morphism, you associate the same bimodule. And this bimodule is exactly this internal point. Okay, so you see, you forget a lot of information here, because all morphisms go to the same stuff. And so it means that to any surface as algebras, you have this, okay, because T tensor G goes to L tensor G by Kerler-Lewashenko, and then by the vertical arrow, you go to the internal and. And for bimodules, it means that for cobordisms, it means that for any cobordism between two surfaces, the stated skein space of the cobordism as a bimodule it is actually just an internal home. So when H is factorizable, which is this non-degeneracy condition, and finite dimensional also, actually you see the stated scale bimodule does not see the topology of the cobordism actually. Whatever cobordism you take, you get at the end the same bimodule. Yeah. And yeah, there was some point of the proof, but yeah, my point of the proof may be this isomorphism between stated scale space of surface and endomorphism of the Cohen. It is deduced from something which is called arXiV isomorphism, and which comes from the theory of quantum character varieties. And then then you can deduce that any bimodule is a sum of this kind of bimodule, because these algebras are very rigid. These are matrix algebra, right? And then by topological argument, you count dimension, and you show that actually this direct sum disappears. There is just one submap. And I will stop. Thank you.
Any questions?
Most structure your cobordism also state arcs and so on, but at the end it doesn't see any topology.
No, it does not see the topology. When it is factorizable only. This is very a result in the factorizable case.
But you need factorizable if you're
For Kerler Lubashenko, yes. But for stated scale, you don't need. You can do stated scale for any ribbon of algebra. So you have more stated scale functors than Kerler Lubashenko functors.
so do you have any results that it's more interesting if you're non-factorizable?
It's hard to compute, so it's hard to transfer, of course, especially the bimodule structure. Maybe the case where it is easier to see it is when it is finite dimensional, because here you have basis of the cobordism. Maybe finite dimensional and not factorizable. Here it can be interesting, but not factorizable. Because if it is factorizable, you lose all the information.
I still have a question about this. I want to understand this bimodules. If you take, say, H just a Swidler-Hopf algebra, can you kind of describe this category? Like, I mean, is it finite, many objects, or many simples? Is it abelian? Is it abelian, by the way? Or no, it's not really. Right?
No, because
It's Morita kind of category, right?
Yes, it's Morita category.
But like for Swidler, can you say something? It's nice Riemann-Hopf algebra.
Do you have classification for algebras internal to Swidler? Yes. See,
Maybe it's not a class, or because you ask conditions, right? You ask this. You say basically any algebra, it's object any algebra with this quantum moment map.
yeah, but if you forget the quantum moment map, just the target category is just all algebras in H-mod, okay?
Yeah.
And all bimodules internal to H-mod.
Yeah, okay.
But even for Swidler, I don't know what are algebras internal to.
Oh, we don't know what algebras even in vect, right?
Sure.
Yeah, okay.
No, but I think
it's big category.
You can look examples. Yeah. But then for the quantum moment map, in the factorizable case, maybe a comment. In the factorizable case, it reduces to a much older notion, which is due to Varaniolo and Vassoro and Lou also. So when H is factorizable, a quantum moment map is just an algebra morphism from H to A. So here it is really H, it's not the Cohen, and satisfying this condition. If you take an element in A and you multiply by mu H, then you must have this. So A is an algebra in H, okay, so I can act on elements of A, and you have this condition. And you see this condition, it can be rewritten in this way. Probably with a mistake, but let's say this. Okay, probably this one. By using an antipode axiom. So you see a quantum moment map, it is just a map which entirely characterizes the action of H on your algebra.
Internal.
And you see, if you know the quantum moment map and the multiplication in A, then you can recover the action. So this is the initial definition of quantum moment map. It is a map, it is an algebra morphism which entirely characterizes the action of H on your algebra. And when H is factorizable, this definition is equivalent to Safronov definition. So you can imagine it this way. This is a map which entirely characterizes the action of H.
Does it make sense to restrict just to some class of A's, like simple algebras? Or you want all algebras?
For our category, no, all algebras. But again, when it is factorizable, you can restrict to simple if you want, because you learned in matrix algebras. See. So for factorizable, you can restrict the category to simple algebras. This is exactly what this theorem means actually.
I see. So even the image will be just simple algebras.
Yeah, just objects actually.
Can you maybe, because bimodules would naturally want to be a true category, right? So can you somehow enlarge in this framework, and this might see something more, because you still take ISO classes of bimodules.
Yeah, so this is a point. So this is what I was discussing during lunch with Christophe and Lucas. Yeah, so maybe the point is that you have to consider two categories.
Yeah.
Right. So you take object algebras, morphism bimodules, and two morphism, isomorphism of bimodules. And then I think this functor extends to these two categories. And then at the source, you have to take surfaces, cobordisms, and diffeomorphisms of cobordism. And most probably this functor extends to this. Yes.
Could you maybe go even further, and instead of just diffeomorphisms, take bordisms over bordisms, so some form manifolds with corners, and this I don't know.
Good dream for
that. Dream.
I just want to make a comment. Your question, Azat, is basically asking whether we know a classification of the module categories over the suite representations.
Yeah.
The answer is not. I mean,
Like
no,
so
Shimizu's
simple one,
work-
exact ones we know.
okay,
Exact ones we
so
know.
for Sweetler.
Procedure,
Okay.
yes.
Ask Martin.
Okay, great.
Yeah. Even for
So-
more complicated, even for small quantum groups, you know.
Yeah, that's Shimizu's, for instance.
No, but first was Martin.
Okay. Right.
Okay. Are there other questions? Okay, thank you, Matya. See you tomorrow.